Good afternoon, everyone. Today, I'm going to present our collaborative work with Natalia Lukashevich on fine-tuning large language models for the hypernym discovery task, with special emphasis on one critical consideration. And I'll begin with defining some key concepts related to our field of research. Hyponymy is a known as is-a relationship that exists between a more general and a more concrete term, like between concepts animal and dog. Here, animal is the more general term, the hypernym, and dog, a more concrete term, is its hyponym. Co-hyponyms are referred to two items that share a hypernym. Hypernym prediction or hypernym discovery task is a natural language processing task that involves predicting one or more hypernym for target input. And this task is particularly important for building taxonomies, structured sources of data based on is-a relationship. On this slide, you can see an example of a taxonomic subgraph. Here, the superior nodes are parents to inferior nodes. They are hyponyms, and the items on the same line, the dog breeds here, are co-hyponyms or sisters to each other. Oh, sorry. Taxonomies offer numerous practical applications, but one of the most significant is their role as serving foundation for building ontologies, even more complex data structures that encompass various types of semantic relationships. Notable examples of ontologies are semantic web, the databases that form the backbone for semantic web, WordNet, often referred to as linguistic ontology, and Wikidata. Large language models achieved remarkable success in a variety of natural language processing tasks, and hypernym discovery is no exception here. The state-of-the-art approach proposed by Moskvoretskii and others takes advantage of using a model based on LLaMA 2 that is fine-tuned on a sample extracted from WordNet, a standard source of taxonomic information for English. The authors meticulously removed test items from the benchmark they evaluate the model on from the training sample. However, they do not treat the co-hyponyms or sister terms the same way. In this talk, we will show that the co-hyponyms introduce another kind of bias, so removing only test items is insufficient. This is particularly important for real-world applications for taxonomy construction and enrichment, because the developers of taxonomies do not always know if the co-hyponyms for the item they want to add to the taxonomy are present or if they exist at all. Moskvoretskii and others also argue that adding definitions during initial fine-tuning improves the model performance. So building on this insight, we are ready to formulate our research questions. The first one, does the presence of sister terms enhance model performance? Second, does the presence of definitions on sister terms affect the performance? And the third one, how does the absence of definitions for sister terms affect the model performance if we train the model on samples with definitions? Now, let me describe the dataset. Following established tradition, we use the 1A English dataset from Samuel 2018 competition, where hypernym discovery was first introduced as a shared task. This dataset includes 1,500 hyponym-hypernym pairs for both training and test set, and the target hyponyms, the input hyponyms were extracted from a large text corpus, while the ground truth hypernyms were sourced from WordNet and other taxonomic resources. And below on the slide, you can see entries from this dataset from the test collection. As for evaluation, two main metrics are used in these tasks. Both came from the field of information retrieval, mean reciprocal rank and mean average precision. For the purpose of this talk, we will concentrate on mean reciprocal rank because it has a more straightforward interpretation, as it denotes the average reversed position of the first relevant item in the list of model predictions, and also no significant difference were observed between the results measured by MAP and AMRR. And you can see the formulae on the screen. So now let's examine the SOTA approaches. On the left side, you can see a table from the paper by Moskvoretskii and others. Here you can see the results of the TaxoLLaMA approach compared to previous approaches. TaxoLLaMA bench refers here to the model trained on the sample from which test items were removed. And fine-tuned indicates that the model was additionally fine-tuned on a specific data set, 1A English in this case. And on the right side, you can see the results of the very recent approach proposed by Liu and colleagues this year. While their approach achieves marginally greater metrics than TaxoLLaMA, it comes at a higher computational cost. This approach leverages from using a popular supervised fine-tuning method on self-generated taxonomic entries. We have not been yet able to validate our hypothesis on this approach. However, we propose that this approach is also susceptible to what we refer to as sister bias. So for the remainder of the talk, we are going to concentrate on the TaxoLLaMA. It uses Llama 2 as the foundation model and is specifically designed to address four lexical semantics tasks related to taxonomy, with hypernym discovery serving as a cornerstone. Another advantage of this approach is its computational efficiency, because one can run fine-tuning of TaxoLLaMA with low-rank adaptation and 4-bit quantization, even in such resource-constrained environments like Google Colab. This model is available on Hugging Face data repository. As previously outlined, the pipeline for the training of TaxoLLaMA involves two stages of fine-tuning. On initial fine-tuning, we train the model on the sample from WordNet, and this is followed by the secondary fine-tuned on specific data set, the 1A English in our case, and we evaluate the model after both stages. Now I will provide a brief description of the sample construction procedure we use. To address to our first research question, we needed to compare equally sized samples with different types with the removed nodes of different type of semantic relation to the test items. Co-hyponyms, only non-co-hyponyms, or random items. And to achieve significant results, we controlled for 4 different proportions of removed item. We set 100% proportion as the total number of items, including sister nodes, for all proportions, and we gradually, incrementally decrease this number by intervals of 25%. We also use fourfold cross-validation for 25, 50, and 75% proportions. That means that we compose the set for removal from varying shards of size 25%. And this gives us 4 samples for 25 and 75% proportions and 6 pairs of shards for 50%. We also normalized the shards by the number of items associated with co-hyponyms in co-hyponym condition, and the shortest path to the nearest test item in the non-co-hyponym condition. As for random condition, we use 3 random seeds to assemble our samples. This experimental setup yields 42 samples across all conditions and proportions. And now we can proceed to the results. Depicted here is the line plot. You can see that it's evident that the performance of models or the model where cohyponyms were removed is lower than the performance of the model where non-cohyponyms were removed, if you compare the blue line to the red line. As for the random condition, the actual number of removed sisters were from 8% to 29%. So it reasonably explains why we observe the metrics marginally greater than those for cohyponym condition for 0, 25, and 50%. It's also worth noticing that the relationship between the proportion and the metrics is nonlinear. So this suggests that the relation between the size of sample and the performance of model is not straightforward. On this bar plot, you can see the results of the model after the secondary fine-tuning, with the blue bars depicting the gain the model achieved after the second stage. And as you can see, the results across all 3 experimental conditions do not differ so much. This suggests that the gain the model achieved in the non-cohyponym condition is smaller than the one it achieves in cohyponym condition. So this suggests that the gain the model can achieve after the secondary fine-tuning is limited to a certain extent that is independent of sister bias. However, it's important to note that Semmelweis dataset itself contains a small number of cohyponyms, about 3%. So it's plausible that the difference we see here is the result of these 2 biases overlapping after the second stage. But this being said, that's just a hypothesis that we have not yet been able to verify. These 2 slides, I will skip these slides because they summarize the point I have already discussed. And now we can address to our 2 next research questions concerning the samples with definitions. And here we use two complementary strategies. First, we can selectively add definitions to nodes with specific type of semantic relation to the test nodes, co-hyponyms, non-co-hyponyms, random, similarly to the previous experimental setup. And conversely, for the second strategy, we can explicitly exclude definitions from a given type of taxonomic relation while providing them to others. And here as well, we control for four different proportions. And here are the results for the first setting. Here we see the difference only at the edges, at the lowest and at the highest proportion, especially at the highest proportion where the metrics for the co-hyponym condition decreases sharply. This can be explained by the fact that the form, the sister nodes are presented during the initial fine-tuning here differs significantly from the way they are presented during the second stage and the evaluation, because no definitions are provided for the semi-val dataset. So here it seems that the model is unable to retrieve the important information from its memory. As for the fine-tuning, the previous generalizations and observations seems to hold for this condition as well. So this suggests that there is a complex interplay between different factors, the size of sample, the type of nodes, and absence or presence of definitions. So this complexity requires further investigation. I'll skip this slide for the same reason. And now we turn to the results of the final experimental setting, the removing of definitions, and here we can see a significant gap between the co-hyponym condition, which is superior to other conditions. The explanation is in fact the same as for the previous experimental setup, because here co-hyponyms are presented within the prompt in exactly the same format as they are during evaluation and secondary fine-tuning. And again, nothing special here. As for the fine-tuning, it seems that the relationship between the dependency between the gain the model achieves after the secondary fine-tuning and the metrics after the first stage are inversely related. The lower the performance, the higher the gain is. And this slide, I will skip this slide. And now it's time to draw conclusions. We demonstrated that the sister nodes really introduce a form of bias that is particularly crucial for real-world applications for taxonomy construction and enrichment. Although it seems that additional fine-tuning can mitigate this bias, that does not diminish our finding because such a fine-tuning is not always feasible in practical scenarios. And additionally, there's another approach that the authors of TaxoLLaMA did not consider. We can train the model on the so-called diachronic WordNet datasets, which involves an older version of a WordNet or a similar taxonomic research for the training set, and the notes from a newer version of the same research for the test set. And this kind of data sets seems to be unbiased, because the procedure of collecting the samples here are chronologically related. So it's a natural way to construct the data set. And on this slide, you can see the answers to our research questions. And here on the screen are the papers we referred to during the talk. That's all for today. Thank you for your attention. I'll be grateful for any questions or comments you may have. Thank you.
Thank you, Fedor. First of all, I would like to say thank you for the color scheme you choose for your graphs. That's really nice. Do you have questions from the audience, maybe? Seems to be not yet. So I would like to ask a question myself, maybe. So you're describing that you like measuring biases in this how to say it, twin terms. Am I right here?
This is the terms you mean?
Yeah, it's wrong word, sorry. And you measuring biases, and you mentioned that these biases occur like on the temporary related corpora. Is it really important feature of a corpora, this temporary temporal link between the data samples? If we remove it, does it change something here?
Yeah, thank you for the question. It matches more the natural way the taxonomies are constructed in practical application, because we often have an existing taxonomy, for example, in production that we want to insert some new item, for example, for new products, and here it's a natural way to use all nodes we already have as our training set of a reference point, and the new nodes that we want to associate with one of the nodes that are present already.
Okay, thank you.